Jebale Jebale to all of you, Jambo, Hotep, Akwaba to you all. So I am Dr. Marcelin Inidabo, an African from Senegal in Ziguinchor, the small city of Tilen, where I learned to play in soccer some years ago. But today I will not be talking to you about soccer and other stuffs also. I will be talking to you about second order dynamical systems. I am a PhD on control systems, a consultant engineer in industry, and an independent researcher. If you want to be in touch with me, please send an email at contact@daboacademy.com. Okay, so I have been since some videos talking to you about specific concepts on first order dynamical systems and second order dynamical systems in the sense of ordinary differential equations. These equations, as you know, are specific, so I use the constant coefficients one. And I treat these problems according only to the in terms of time, okay, not in terms of transfer functions or frequential domain. I treat these questions only also for stable systems, okay? So the concept that I am going to talk to you today is the design of a second order system, but I will show you that it is not because a second order system has a smaller damping ratio that it is faster than that of a greater damping ratio, okay? And we'll just give to you a comment about some, coefficients. People talk about 0.7 and then, or 0.43 when you buckle up your system, when you do a closed loop. But we will not be talking about that. We will just remain on the open loop systems. But when you take the 0.7, people say that it is faster than, let's say, 0.8, for example. We will see in which condition it can be faster. Okay, and then it is also possible to have a system that has a greater damping ratio and that can be faster than a system that have a smaller one, right? So I will show you as you do it because I have derived some formulas and these are thanks to my vision, and I thank the Holy Spirit, I thank God, I thank Jesus Christ, my God, my Savior, for having revealed me these kind of things in this control system dynamics. Okay, so now what to say? When you are, I invite you to watch the previous videos and just a brief comment on what I have introduced in modern control systems, because this doesn't happen previously in the whole history of control systems. I have never seen them, but any problem, if you have seen them before me, please let me know and I will be happy to take the references and compare with the results that I am sharing with you today, right? So I have introduced for first order dynamical systems in the sense of ODEs, a criterion of identification, very simple, based on the ratio of their time responses. So I invite you to go to my previous videos, to the channel, okay, my channel. Please like, share, and then subscribe. And so click on the bell in order to be able to receive different videos that will be very helpful for you. I hope so, right? And then, so from there, what I have done also, I have introduced in control systems for second order systems particularly, that there is only one time constant, okay? That is the double of the relative time constant, is also one vision and one concept that I have introduced, okay? So the concept of natural time constant, the concept of time constant of the surface time, the concept of relative time constant, as said, the concept of only one time constant for any given dynamical system of second order, right? And then from there, I have introduced and discovered a new criteria in order to identify a second order system only based on the ratios of their time constant, okay? So I will not say more. I just invite you to go to the channel, check the previous videos, and you will find videos, for example, titled One Single Time Constant, for example. Check that video carefully, and then you will understand every concept and much others also that I have introduced and all the explanations that are going with it, right? So now, as I said, today I am going to talk to you in this video about the design of a second order system, and I will show you that it is not because a second order system has a smaller damper ratio that it is obligatory the faster one. Okay, so now let's go. If you have a second order system, this is of course a static gain. This is what I call the natural time constant. This is what I call the constant time constant of the square surface, okay, of the surface of time, the time constant of the surface of time. And then you know that if you have a second order system, you have different cases for the responses that are given here. And then here is a case for a first order dynamical system. The definition that I have introduced for the first time in control systems is this one, that any given dynamical system has only one time constant, that is here, okay? So now let's go. If you consider this one, right, the t minus td is a multiple of the time constant of our dynamical system, you will have a function, percentage function, as showed in previous videos, that is equal to this expression where you have alpha is a parameter and xc also, the damping ratio is also the parameter. Going from here, what we have done, I have derived tables, different tables, through which I give to the engineer or I give to the researcher or a designer very powerful tools in order to make its own design. And the tables are here. How do you read this table? Here you have a damping ratio in the first line, and then you have the overshoot that you can have here. The DEP stands for dépassement in French. That means overshoot. The first overshoot, okay? And then for different damping ratios here, you have the overshoots. Don't get confused because here you have negative sign. It is normal because I work with an autonomous system to give these expressions, okay? And it will be the same here also, okay? So you have two steps, kind of two tables that are one on top of the other. And then here for the first table, you have the time response or the rising time, rising or fall time between two percentages of the initial condition, okay? And then if you want to know deeply how I put this initial condition percentages, please watch the previous videos. I go deeply in the details, okay? If you have the same result, if you want to have the same results for systems with initial response, I just invite you to take the complement at 100% of these percentages. Okay, so refer to previous videos. So now when you take this t minus td, that is a multiple of this one, you have here, okay, the tau s, that is a definition here. And then by taking the alpha r that you multiply by 1 over c times omega n, I put that a capital A here of xc is equal to the alpha that you define divided by xc. And this alpha divided by xc is what you have here, okay, for example, for the Xi that is 0.15, the A, capital A of Xi is 1.513. This is what you have here. And the omega n that you have is the omega n times the difference of time, or the relative time, okay, at which you want to compute the response of your system, for example, okay? And then, so how can you use this table? Let's say that you have a damping ratio that is equal to 0.4. And then you know also the natural pulsation, and then you want directly to compute the rising time, the rise time of between 5 and 95%, for example, of your equilibrium. How will you be using it? You will say just that this time is equal to, I say 0.4, it is equal to 1.718 divided by your omega n, and then you will be having directly your time response. I repeat, you go, if you have a system that has a damping ratio of 0.4, and then you want to compute its time, rise time, between 5 and 95, how you compute it? If you know it's omega n, you just take 1.718 divided by omega n, that you know, and then it will give you this, okay? If you want to do it with other times, rise times, you can by the same way. And also, if you want to do it for the rise time, for example, at 95%, you just take 2.05 divided by its own omega n, that is its natural pulsation. So this will give you the time response at this value, etc., for different values. If you don't have, if you have a damping ratio that is different of these values, it is easy to derive also the corresponding alpha from the formulas that I have shared with you. Check please the previous videos where I explain the design. Now it was a previous video where I explain how I compute, I call them Dabo's formula for time response. Okay, so if you check that video, you will see in details how to compute the corresponding alpha, and then for that alpha, the corresponding alpha to a given percentage, and from that value, you divide your alpha by your Xi, and then from there you will have your capital A of Xi, and then this will be very helpful for you. Okay, so I hope that this is clear for you. This table, how do you read it for Xi equals 1? You just consider that here, all the time that you have on the first line are equal by column to the expression that you have on the second row. For example, this one, T rise time of between 98 to 2% of the initial condition is equal to 5.618. And this is the same thing for all of them. At the left here, you have the rise time, and then, or the fall time, and then here you have the response time, okay, at a given percentage of the initial condition. Again, take the complement at 100%, and then you will be having the corresponding time response for an initial response. Okay, so here you read it in the same way as the previous. Let's say you have 1.75 as damping ratio. Or if you want, you just take 1.1 for damping ratio. And then the rise time between 90 and 10, or the fall time between 90 and 10% of your initial condition is equal to 3.864 that you should be dividing by omega n here, right? So you have the Xi, and then you have the omega n. You can compute directly the temporal performance of your dynamical system, okay? In another way also, if you want to do a design of your system, how you derive it? You say, okay, I want a system that doesn't have an overshoot, for example. And then you will be in the case of this table, or you can add the case where the damping ratio is equal to 1, for example. But if you just consider this one, you can choose one of these different damping ratios. And then when you choose 1.1, okay, and you want a rise time that is fixed equal to 1 second, therefore, the omega n times 1 second is equal to 3.864. Therefore, the omega n that you have to choose is equal to this value. Okay, you see, it's very simple. This is a table to compute the time response. If you know, sorry, if you know your damping ratio, and also you know your natural pulsation, or if you know, for example, your damping ratio and then you know your time response, you will be able to compute directly your frequency, okay? Because the omega n is 2 times pi times the f, okay? That is the frequency. So this is how you use this table that I have introduced in control systems. And then for any given, for any range of the damping ratio, meaning for overdamped systems, you can use two tables, the one for the rise time and the second one for the time response, okay? So I guess this is clear for you. I hope it is clear for you. Okay, if you want to have more explanation, for example, look, here it is a table for the rise time. So the time between 2 percentages of the initial condition. The expression of the left, omega n times t, is equal to this constant when you are in the case of this damping ratio. Okay, this is how you should use this table. This one, this product, omega n times TMD 80/20 is equal, for example, to 3.361 if you use this damping ratio. And of course, it is equal to 2.902 if you use this damping ratio. So you should know in which damping ratio case you have, which omega n you have, and then you can compute the performance, temporal performance. If you are in the case of time response, it is the same paradigm, the same philosophy, okay? So now let's go for a given example. For example, here, let's go to check the software for simulation. So in this case, let me present you very quickly this example. So here, what we are doing is that we have different damping ratios on this table, okay? For these different damping ratios, the table I have previously presented you, I pick from there the formula for the time response, and then what we have there is here, okay? We have the different formulas, okay? For the different damping ratios. Each damping ratio with its own formula as a time response at 90%, okay? For an initial response, of course. So this I give you for free, but don't forget that all this information are resumed in this book. This is the French version, as I always say, and the English version is coming very soon. So prepare yourself to buy this book because there are details inside that that will be very useful for you. Okay, so now let's go here. What you have here is a formula to compute at 90% the time response for the different damping ratios, right? And then from here, we will consider if you want, I desire, for example, T90 for a damping ratio system of 0.25, that is equal to 3 seconds. And then what I will do is just which omega n that I should use to reach this, okay? So I should use in reality this formula that is 1.728 divided by omega n equals 3, and then the omega n equals 1.7028 divided by 3, and then it gives me this omega n, okay? So for this one, what you have here, right? This one. So the omega n is, if I have this one, I use this omega n, for example, and it will give me this time response at 90%. Same philosophy as for this. Okay, so now let's go for simulations. Let's go for simulations. Here I have my dynamical system here, as you know. If you want to understand the simulations, I invite you to look at also the previous videos and you will see what I'm talking about. Sorry, let's go for this. We consider this one, and then I show you again the presentation here. So you can see the damping ratios that I have. They are here, 0.25, 0.8, 1, 1.65, 1.9. And then if you consider these expressions that I have prepared for you, right? Okay, you will have their corresponding time responses that are here. Okay, so let's go for simulations. If I click on evaluate, it will plot one by one because I have a pause function that is here just before the end. So waiting for the system to simulate and plot. And I will show you what we have as a response, okay? So recall that, don't forget that the responses are given here. Okay, are you giving me the plot or not? It seems that there is something wrong for the simulation. I don't know. What's going on this simulation? I don't have a plot. Okay, anyway, so now I stop again. Let me just check here. Okay, I have a figure. So I go back here. Do again the evaluation. So I have the plot, okay? And then why did it didn't work the first time? I don't know. Now I consider this one. I am supposed to have 3, okay, at 90% for the first plot. The first plot is when you have an overshoot, when you have a damping ratio of 0.25. So let's go. We put it here. We are going to look. We're going to put a tip here. Look at 90%. 90%. Here we have the result is as X corresponding to time response is 3. That is what we have exactly here, 3. Okay, so you should look at this first column for the next presentations. And then, so from here, let's go for the next. I just press a button. And then the response that we have should be 2. So we check here at 90%. Around 90%, and then we see that we are not far from 2. We can see if I reduce it to have the most accurate expression, the most accurate expression that I have here is is 2. Okay, it is what we have here. Okay, if I press again on the button, the third one, we needed 1.5. Okay, so we are not far. Let's go to reach it. So we are looking for 90% of the initial of the equilibrium, and at that value we are supposed to have 1.5. Okay, that is 1.5 seconds. Second, that is the value that we want to have. It is what you have here. Okay, and this is what you can see here. The next plot, we are supposed to have the value 1. Okay. So you see that you have quite 1 here. That is given at this position. And then the last one, you have 0.5. This is what we are supposed to have Okay, so now let's check. And then go further. We have 0.5, okay, as expected here. So we can make a design of dynamical systems. And what I'm showing to you that is that here, I told you that when it is not because you have a smaller damping ratio coefficient that you can obligatorily be faster. It will be the case because when only if and only if here you have, okay, the same omega n for all of them here in this expression, okay? Effectively, if you have the same omega n here, the ratio will be proportionally quite the same, okay? And then you have a greater coefficient, a smaller coefficient here, to a greater coefficient here, and these coefficients will just correspond to a given value to compute the time response, okay? Because it is a time response. And as the time response is smaller, the system is faster. This is what you can see here. So now let's go, I show you. You will be seeing, if I put the omega n that is constant, this oscillating value, this oscillating curve will start first in terms of time response, and then you will have the others less oscillating until it is overdamped, okay? And the overdamped curve will appear later, right? So let's go and do. I have prepared something for you here. So if you are curious, you can check also the video in French. I think it is quite the same, but maybe you will find some other complement of information because I sometimes don't give exactly the same stuffs in the two videos. Anyway, and it will be the opportunity for you to hear some French words also if you want. So let's go. I stop the simulation. And then here, let's go for a new simulation. You see, this is the first one, okay? If I press OK, you see the second one, okay? The second one is slower than the first one, as you can see here, okay? Because this value is greater than this one. And for the third one, you can see also we are going slower and slower according to time, okay? We go again, and then we have this one, 1, 2, 3, 4. The last one, 5, okay? And then you can see it goes from the smaller damping ratio to the greater damping ratio. But there is another thing also, good news that I want to tell you, is that when you do this, you can directly also compute at which value of time that you will reach at 90%, for example. This is the case to use here. Let's consider this formula, okay? And then check which value we will be having, okay? This is the last one. So let's do this, put this value here. It is divided by omega n. It seems not to work. Let me just check here. Okay. So I am obliged to stop it like this. Okay, so MATLAB has some problems now. So you see, you can see I can compute directly here. Okay, I have a tip. I can compute directly here the values that I have. Okay, for example, you take 728, and then you divide by the omega n. I wanted to show you 728 divided by omega n1, and then you have this value. If I consider the last one, position 5, I will have this value, okay? 0.8064. Let's go and check that. This is the time response I will have for the first at position 90. Okay, if I come here to check, %90%, you can see that, okay, with this one, I have 0.864. That is quite the same as here, as for computed from my formula, okay? So now let's go now and do something else. I just want to show you something else. Look at here. Any given damping ratio that you can have, let me show you. Any given damping ratio that you can have, okay? You can be able, thanks to these formulas that I have computed for the first time in control systems, you can compute exactly the omega n that will give you at 90% the time response that you want to have. Okay, so now let's go for this. The values of the time response are here, 1.728. The omega that is giving me, that is this one. I have prepared something to earn time. And then, so this one I will comment. And now when we go for simulation, you will see what we have. So first we have this one. The time response at 90% of the equilibrium. We will see how much it is. If we fix ourselves at 90%, you can see that it is quite one, okay, as expected here. And then let's do for the next. The next curve, you see that it is going at 90% through one. And as I told you, all the responses will go through one, okay? The third response, you see that its time response is at one. So you can see all of them are at one, okay? So this is what I wanted to show you that it is possible to make the design that you want to make. There is no constraint, in fact, if you don't care about the omega n. But if the omega n is a constraint for you, of course, you will be in a certain constraint also. You will be obliged to choose a specific damping ratio in order to reach your performances. But if there is no constraint on your natural pulsation, meaning on your omega n, it will be easy for you because you will have the choice, okay? You will have one choice with your damping ratio. For example, you say, I need a dynamical system. For this example, I am telling you, I need a dynamical system with an overshoot that is around, let's say, 0.46, for example, okay? So 46% of overshoot, okay? And with time response at 90%, that is equal to 1. So in order to achieve this, you will choose a 0.25 and then omega n that is equal to this value, 1.728. If you say, okay, I don't want an overshoot of my system, I just want something with a time response, okay, that is always at 1, but I don't need an overshoot. So you have the choice. You can take this value. You can take a damping ratio that is equal to 1.65, as you see in the different values. And then also with its corresponding omega n, and you will have the same time response while avoiding your overshoot, okay? And your system will respond smoothly to your desired performances. And then you can do also as a test, etc. So please check these values that I am giving to you here. You can make your exercise, your own exercise. Your formulas, the formulas that I give you for free are here for free. And then, of course, I share these results that I have discovered with you, okay? If you use these formulas for these values, you will be able to compute the time response of your system at 90%. And then if you want at 95%, the formulas I give you for free are here. Don't forget, the book is coming in French and in English. So prepare yourself to buy this book because there are so many good results that are inside and that can be very useful for you in order to deepen your understanding or in order just to see, to have another vision of control systems. And this can open a wide space or a wide range, okay, for you to explore. Okay, I think it can be very benefic for you. So the formulas are here. You fix your desired time. You derive your consequent omega n that will give you your desired time. Okay, so here you can put whatever result you want. Instead of 3, you can put 1.2, 1.02, and then you will be using this formula 8.804 divided by the time that is here. It will give you, of course, the corresponding omega n. So you can use this. These are the desired values. You do like you want, because you want a desired value of time. You will have it here. If you want the desired value of omega n, you fix your omega n that you want to have, and you will see the consequence on time that you can have by using strategically this formula also. And you do it for another one also. You can put here the values that you want. It's up to you. These are the formulas, I say again, for the time response at 90% of the equilibrium, time response at 95% of the equilibrium. Here, I share with you also the rise time. If you want to have a rise time, desired rise time that you want to have, and compute the corresponding omega n, the formulas are here, okay? If you want to do same thing for the rise time between 5 and 95%, formulas are here for these damping ratios, okay? So now I let you exercise yourself. I thank you very, very, very much for having take your time to watch this video. I hope that this has been a very wonderful journey. And then for you, okay? So I am waiting for your feedback. If you want to contact me, please don't forget. You will be able to do it via contact@Dabo Academy, which is here, okay? daboacademy.com. Thank you again for watching. And then please enjoy, like this video, subscribe yourself to the channel, and then share. If you are a professor, please share with your students. If you are a researcher or professor, an engineer, please do the tests by yourself. And then share with people around you. This will allow me to develop and you will be supporting by doing so my job. So anyway, thank you again very, very much. And then I guess I will be able and ready to do another presentation for you very soon. Enjoy your day. Enjoy everything that you are doing. And sometimes life is tough, but don't forget, please, stay firm in the grace of God. Thank you very much. Ya jëfate sama gaay maa ngi leen di nuyu bu baax a baax di leen gërëmati gërëm. Waaw, ñu déggante ci fan yi. This is Wolof from West Africa, Senegal, where I come from, and a small word in Creole. Mantenha pa posturu kuna jobi video li. Kabo diskisi, bo fasi, bo partilial pa outro gente stambi, pe pudi receiving un bon information cosina pudi judelis. Na se trabalhos tudo que é na fasi. This is Creole from Ziguinchor, Senegal in West Africa, as I am an African from Senegal. So looking forward to hear from you soon. And I say, webale siabonga gakulu. Bye.